Hi there, today I wanted to look at how to find arc length. So let's start with this function, f of x. If we wanted to say, for example, know how long this function is from here to here, let's make it a little more obvious by drawing a point from here to somewhere, I don't know, let's say here. How do you find this length here? Well, one way to start, it might be to maybe draw a line, right? Now that line, what we can do with it is we can use the Pythagorean theorem to find how long the hypotenuse is. Let's see, let's say somewhere there, and then we draw a triangle from there. Well, it should really be a right triangle, but let's see, there we go. We can draw a right triangle. This is not a right triangle right now, but we can draw a right triangle, and that will let us find this hypotenuse here. But the problem is, as you can see, it would only be an approximation because this line is not exactly the same length as this line. This line is a little longer because it bends downward. So how will we then find this length? Well, let's start with the approximation, right? Let's write it out. So now I'm here and I'm gonna try to draw a function, and this is not necessarily the function that I drew earlier or that I plotted earlier, right? But let's say so go something like, I don't know, like that. We just need some generic function, right? Now, we had 2 points, a point here and a point here, right? From these 2 points, we can draw a right triangle. Sorry about the bad drawing. And now, like I said, this is only an approximation because this hypotenuse is not going to be exactly the length of this segment here. So the approximation goes like this. Our function is f of x, right? So this is y and this is x here. So if we choose some point, then we would know that that point is here, x1. And then if we choose a second point, we can choose those points arbitrarily, right? It's any point that we can choose. Let's call it x2. Now, to find the other coordinate for both points, we put it through f of x, right? So then this point goes somewhere here, and let's call that y1. And this point goes somewhere here, where is y2. The x points we can choose arbitrarily. Now y1 and y2, that's sort of determined by the x1 and x2 that we chose. So y1 really is equals to f of x, well, f of x1. And similarly with y2 equals f of x2. So that's the coordinates for our point, right? And so we're able to determine now this distance here. And that distance really is just x2 minus x1, right? It's the difference of x2 minus x1. The same thing here. This distance would really be y2 minus y1. But we know that that's used f of x2 minus f of x1. There we go. So now we have both of those distances, and we know that the Pythagorean theorem is something like c squared equals a squared plus b squared. In this case, doesn't matter which one is which. Used for the future, just to make it easier, instead of using c, I'm gonna use s. And so in this case, we can solve for s or c. It's equals to the square root. We take the square root of both sides, and we're left with a squared plus b squared, right? I also want to change what y2 minus y1 is, and I'm just gonna call it delta y. So it's not two things, it's one thing, just delta y. Similarly here, I want to call this delta x. So it's the difference, right? And so I can plug these numbers in. Again, it doesn't matter which one is which. I'm just gonna say that a is delta y square, right, plus delta x square. And for now, something that I want to also do is I'm going to call this delta S. The reasons are going to become obvious later, but for now, this is just delta S, just to make sure we understand what this is. Then delta S is equals to delta Y squared plus delta X squared. And this is the approximation. That's it. This is how we would be able to approximate what this little segment of this function would be. We can choose, the points that we choose are up to us, right? So we know what delta x is from here. We know what x2 and x1 would be, and we would be able to find y2 minus y1. So that's the approximation. But again, it's an approximation because this line, let me use a different color. This approximation here, it's not that the red line is not going to be the same. The hypotenuse is not going to be the same as the actual function, especially for functions that differ a lot more from a straight line, right? We're lucky here that it's pretty straight, but what happens when we choose a point, let's say here, and another one here? Now, that approximation is going to be really bad for this function, this segment of that function, right? So really what we want to do is minimize this length, because the more we focus on that little piece, the more like a straight line it looks like, right? We want to make it as small as possible. We want to make delta x small, and therefore delta y will also become smaller, right? And that just makes it so that this segment here looks even more straight, right? If you go from this segment, the larger one, to this smaller one, it's a better approximation of this part. And if you take a bunch of little triangles, it becomes even better, right? Then you can see, if you have taken some calculus, you can see where I'm going with this. What we want then is to work with infinitesimals. So ds is equals to the square root of delta y, well, not delta y, not anymore. ds equals dy squared plus dx squared. And now, as you can see, now we're working with infinitesimals, and now we can try to rearrange this to make it look a little nicer. We're gonna multiply it by a fancy one. So let's say that we have a 1 here. Whoops, that looks like a 7. And we have dy squared plus dx squared, all under it, the square root, right? We can take this then and make that 1 into a fancy one. And what I mean by that is let's just take that one to be equals to dx divided by dx, right? Dx divided by dx is just equals to 1, like 7 divided by 7 is equals to 1, or a variable a divided by the variable a is equals to 1, right? So I'm taking all of this fancy one, and I'm gonna multiply it by what we have here so far, which is dy squared plus dx squared. Now the thing that I want to do is put this dx here. I'm going to separate these dx's, and one of them is going to go inside of the square root. So when something goes under the square root, I have to square it, right? If I, let's say, have 2 times the square root of 1, to put it inside into, well, this is just equals to 2, right? For this to hold still true and put the 2 inside of it, I have to square it, and that's still the same. So the same idea here, I have to square the dx that goes into the square root, and the one that I'm going to put inside is the bottom one. The square root is equals to 1 divided by dx square. Now 1 square is just 1, so it doesn't really matter. And all of that I'm going to multiply times dy square plus dx square. Now I can distribute this dx throughout. The other dx just stays out here. I'm gonna put it on front, right? And so now I have this, and it will become then dy square divided by dx square plus dx square divided by dx square. And there is the dx outside, right? I just distributed this dx right here among these ones, and so we're left then with the square root of, and the other thing is I can pull out this 2 right here from both the bottom and the top, and that just becomes dy dx square plus 1 dx. There we go. So we're left then with ds equals, I'm gonna rearrange this a little bit so it looks like this, 1 plus dy dx square dx. Now dy dx, we know what that is. Dy dx is just the derivative of f of x. Whoops. Rewriting it, it's then 1 plus f prime of x square dx. Now to make it a little more clear, let's get rid of that ds. How do we do that? Well, actually we need to integrate both sides then, and so this ds would be equals to the integral of 1 plus dy. Whoops, I'm using the other form now, the other notation, f prime of x square dx. And we can integrate this s from 0 to s, which then becomes just s is equals to the integral of 1 plus f prime of x square dx. There we go. And that's it. That's the formula for arc length. This should give us, this is an s, this is an integrand, by the way. There we go. S, usually that's the letter to denote arc length. So s is equals to the integral that is on this side right here. And yeah, so to find any length at all, you just use this integral. And so to show the example then of the other function that we were using earlier, would it truly give us the actual length instead of just an approximation, right? We can try this out. All right, now let's check if what we derive actually works. But let's start by looking at the approximation first between these 2 points. Now I've chosen my x value, the first one to be equals to 1 and the second to 1.5. You can choose any values, right? It's an arbitrary value. So I've chosen those 2 numbers just because they're a little bit easier. So first of all, this is what it looks like, right? This is this segment versus this bottom segment. Now we want to know the length of this segment, right? That's the approximation. And as we can see, the approximation tells us that that's 0.55. That's what it is. Now we know that this distance should be a little bit longer, and so let's check that. So here I am on Mathematica, and here I have created a function, right, that we were working with. I'm also just plotting it just to show it, and I'm doing the integral. So let's check, and actually in this case we did it from 1 to 1.5, right? So yeah, we are checking the length from 1 to 1.5, and as we can see, that's the function, and it tells us that the answer is 0.56. Now compare that to this 0.55. It's not a huge difference in this case because we're working with such small numbers already, but it is significant because this shows us that yes, this arc here, this little piece, is longer than the straight line that we get with the Pythagorean theorem, which makes sense for us because yes, it's curved, so it's longer than the straight line. Anyways, that was it for today. Thank you for watching.